To one and all. Moving forward in the session, today we have reached the third day, and in third day, the first session will be presided by Professor Soumya Gangopadhyay, Associate Professor, Head of Department of Mechanical Engineering, IIT Bhilai. Dr. Gangopadhyay is an Associate Professor and Head of the Department of Mechanical Engineering of Indian Institute of Technology, Bhilai. He obtained his PhD degree in Mechanical Engineering from IIT Kharagpur in 2010. Prior to joining IIT Bhilai, he was faculty member in the Department of Mechanical Engineering, NIT Rourkela, from 2009 to 2017. He also served as postdoctoral researcher at Department of Physical Metallurgy and Material Testing, University of Leuven, Austria, for 1 year from 2011 to 2012. His research interests include metal cutting, development of multifunctional PVD coating, non-traditional machining, material characterization, and thin film tribology. The research activity during PhD and postdoctoral program were related to the development of novel multi-layer and multi-component PVD coating for cutting tools. He has been supervising undergraduate, postgraduate, and doctoral student working in different areas like use of multi-layer coated tools in order to improve machinability characteristic of nickel-based superalloy, mechanical treatment of cutting tool substrate and or PVD coating on their characteristic and cutting performance, powder mixed minimum quantity lubrication, study of surface integrity in electro-discharge machining, powder mixed EDM of superalloy, micro machining, modeling of non-traditional machining process. Dr. Soumya Gangopadhyay has so far supervised 25 undergraduate, 15 postgraduate, and 3 PhD students. He has so far published 35 articles in different international journals of repute and 30 papers in proceeding of national and international conference. He has been currently handling 2 DST projects, one in Indian, Portugal, Bilateral Corporation, and another Advanced Manufacturing Technology, AMT. He has also presented research paper in abroad, one at University of Manchester, UK in 2010, and one at University of California in 2014. Another one at University of Coimbra, Portugal in 2018. Now, I extend my hearty welcome to Professor Soumya Gangopadhyay to preside the session. Today, he will deliver lecture on introduction to micro machining, micro manufacturing. Sir.
Yeah, thank you very much, Dr. Chittaranjan Deo, for your kind introduction and also inviting me to deliver a lecture in your workshop. So now I would like to share my screen. I hope my screen is visible to all.
Yes, sir. Sir, it is visible, sir.
Okay, fine. Okay, so good morning all. As Dr. Chittaranjan has said that my today's topic of presentation is introduction to micromachining. In this topic, I would like to discuss about what is micromachining, what is the requirement of micromachining, what are the applications of micromachining, and what are the broad classifications of micromachining. And then I'll briefly talk about some of the important types of micromachining processes. And then finally, I would like to focus on the mechanical micromachining processes, high-speed micromachining processes, which is a mechanical process. Okay, and that will be also a brief discussion of fundamental concepts. So no research work I would like to present here, because it itself will take 1.5 hours. Maybe in some other opportunities, I would like to present some advanced research work which is being undertaken in the domain of micromachining. So at the very beginning, let me tell you that this concept of this micromachining or micromanufacturing is a kind of modern concept. Okay, in the last 10 to 20 years, most specifically in the last 10 years, lot of research work is being undertaken in the domain of micromanufacturing in general. Okay, but then in India, if you see the scenario, very few research groups are working in the domain of micromanufacturing. Professor V.K. Jain from IIT Kanpur, he actually started the work on micromanufacturing in the domain of electrochemical micromachining, ECMM. Professor Bijay Bhattacharya, who many of you perhaps know him as well. He has good contacts with VSSUT Burla. So he was my master's supervisor. So Professor Bijay Bhattacharya from Jadavpur University, he also introduced the concept of micromanufacturing in India. Okay, it is very important to know the stalwarts or the and very renowned professors or scientists in India who are actually the pioneer of micromanufacturing. Later on, IIT Bombay also started in this domain. Particularly Professor Ramesh Kumar Singh is working extensively in the domain of micromachining, and his area is primarily mechanical micromachining and related domains. Okay, so these are the three primary research groups who are working. In the last 3 years, not last 3 years, I would say last 5 years, rather 5 to 6 years, I also ventured into the domain of mechanical micromachining. When I was in NIT Rourkela, I collaborated with Professor Ramesh Singh from IIT Bombay to start the research work in the domain of mechanical micromachining. And then I started understanding how fascinating the world of mechanical micromachining is, and how it is entirely different from other conventional machining processes. Okay, why I took interest in the domain of micromachining particularly? The reason is as follows. My primary research area is surface engineering, particularly development of advanced physical vapor deposition coatings for cutting tool applications, and of course advanced machining processes. And I think I have given several lectures at VSSUT Burla, particularly in the domain of physical vapor deposition coatings for cutting tools, how the cutting tools perform with the coated tools, and on what are the different deposition techniques, advanced deposition techniques, what are their industrial applications. Some of you, those who attended my previous lectures, they know it very well that I will deliver the lecture on those topics. Now, coming back, as you understand that my interest lies in the domain of ultimately metal cutting, machining, advanced machining processes. And then when I go through the literature, advanced literature, the modern literature, I find that gradually the components which are getting machined are getting scaled down. The components, the size of the components getting scaled down. The dimensional features are getting scaled down. For example, the size of the hole, typically for various engineering applications, range from 5 millimeter to say 50 millimeter. Okay, typically I am talking about a general range. But then there are so many applications which are emerging nowadays, which requires the drilling of micro holes less than 1 millimeter, 1 millimeter, 500 microns, 400 microns, and so on. Some of the examples, okay, are, for example, many of you might have seen the printed circuit board. Okay, in printed circuit boards, to assemble various circuits, we have to have small holes, micro size holes of the order of say 0.5 to 1 millimeter, or even less than that. So people have to do the micro drilling operation on the printed circuit board. This is number one. And number two is turbine blade. Okay, many of you, I hope, are aware of the turbine blades. So in turbine blades, cooling is a challenge, because there is a lot of temperature which generates in the combustion chamber, and then turbine blades are exposed to very high temperature, and then it is a very important requirement to have an efficient cooling. Okay, so this cooling is facilitated by generating the micro channels or micro holes, okay, along the body of the turbine blade. So how to do that? The answer is micro machining. Similarly, in many medical and biomedical applications, okay, so you have definitely heard about the term microsurgeries. In microsurgeries, the surgeons have to take the use of the microsurgical tools for various surgical applications. Now, either to drill hole, to cut some channels, or some other applications. So all those things.
Sir, sorry to interrupt, sir. Sir, slides are not changing, sir.
Okay. No, I was trying to give just a brief introduction, just the background story, and then I would like to go slide by slide.
No.
Okay. So fine. So this is the background. Why we should go for this micro machining, and therefore, and that's why I took a lot of interest that, well, I am working in the domain of say metal cutting in the macro level. I also do non-conventional machining like electro-discharge machining, electrochemical machining, again in the macro scale. But then, there are enough opportunities to work in the domain of components where micro features need to be generated. And it is an emerging areas. And you will not find a lot of research groups still in India who are working in this domain. Okay, there are a variety of reasons maybe, but let us talk about, why we need the miniaturization. I have talked a little bit the background information, the brief introduction of this micro machining. So now the thing is, the less material consumption, okay, during manufacturing. Okay. And so micro machining involves the speed, feed and depth of cut at a very, very low level. Whether you are doing micro turning, whether you are doing micro milling, whether you are doing micro drilling or micro EDM, micro ECM, okay, the removal is amount of material which gets removed is very small, and the features that we need to generate, we can get it by minimum amount of material removal. So the less wastage of material is one thing. Then there are many complex 3D components, 3D features, which cannot be generated with the conventional machine tool, conventional cutting tools. Okay, so traditionally, when you are talking about these 3D components, we take the help of milling cutter. You know, milling operation is a very versatile operations, and there are hundreds of different types of milling cutters that make it more versatile, and virtually any different types of shapes, 2D or 3D, can be fabricated using the milling operations, right? But then it is fine. But then when there are some geometrical complexities, and there are 3D textures, free form surfaces, and that too in a miniaturized form, those actually require the micro miniaturization, right? That requires the miniaturization. Many times these 3D components are not very economical to be generated, to be fabricated on a macro scale. Rather, they are required to be generated in the miniaturized scale. I would not say micro, I would say miniaturized scale. For example, 1 millimeter, 2 millimeter, if it is the dimensional features of a particular 3D components, that is still we call it as a miniaturization, and that can be done by micro machining. Okay, next point is, of course, why we require the miniature small size components, because of the lightness, because of it can be it is portable, okay, without affecting the functionalities, right? And then low energy for device, low energy is required. For example, you have some circuits. For example, the mobile phones. Okay, when the mobile phones were invented or developed, then you have seen the size of the mobile phones, and then their components were also very bigger. As a result, the final product also became bigger. I'm just giving one example, but then there are several examples, right? From the computer to mobile to various electronics gadgets, and even mechanical components which were very big and bulky. Focus is nowadays to have a compact structure, okay, and that is what I mean as the miniaturization. So in many components, when you are actually making the size smaller, it requires low energy for the excitation of the device. Okay, it doesn't bulkier the size, higher will be the requirement of the energy. And then when you are actually doing your work on a very small region, the chance of accuracy, the sensitivity will also you can maintain at a high level. When it becomes a very high, very big, very huge, very bulky, the chance of accuracy, chance of precision, okay, and the sensitivity, everything will be difficult to achieve at a very high level. On the other hand, if it is on the lower scale, a smaller component, it is more easier. Okay. Last but not the least, there is obviously the cost per performance advantages. That means the cost by performance is low, right? Because why cost per performance is low? Because you are downsizing the component, right? But you are actually not sacrificing any functionality of the component. Rather, with the advent of technology, you are product, even when you are making them compact and small size, right? So what is the advantage? Advantage is when you are making it smaller, making it more compact, downsizing, then the material requirement, okay, gets reduced, okay, so the material cost is reduced, and then its performance still can be enhanced, and then it leads to the profitability of the component, right? So I mean, moving on, I mean, in the same direction, okay, this actually shows the biomedical components, right? It is a kind of robot which is being shown here, which actually micro robots. See, I mean, the robotics again is a very good example. In a industry, you might have seen huge robots in the assembly lines and many other applications. And then their size is very huge. Of course, its size is justified for a particular application. I'm not saying that, but for some particular application, you can actually develop miniaturized robots which can be used for biomedical applications. It can take a lot of information as it can be used as a diagnostic tool. In fact, as an advanced diagnosis, medical diagnosis, people are using micro robots for getting a lot of information from the human bodies, from external surface of the human body. Even you will be amazed to know these micro robots can be actually put inside the human body to extract the information from inside. I'm not expert into that, but I mean, I have heard, I have gone through in the journal that this type of micro robots are being manufactured and being used extensively, particularly in USA and European countries. Okay, then these drones, right? I mean, we have initially when the drones were first invented and developed, there was a huge drones to capture, monitor data, taking photographs, videos, etc. So then and drone is a very important product in surveillance, and in many other applications, right? And it is important to reduce the size of this, and then we are having miniaturized drones in many places, many applications. Okay, now the thing is that it makes the systems and the device more intelligent and more autonomous. Okay, it does not require too much of electrical wiring, a lot of connections. Okay, bulkier the component, bulkier will be the paraphernalia. That means the bulk, I mean, more will be the number of the accessories which will be required to support the bulkier system. When you are making it very small, okay, and if you can intelligently incorporate some of the very sophisticated miniaturized components, micro feature, okay, then you are actually making more intelligent. How to make it? I mean, see, I mean, these are the fingertips. The drones or the robots which are being shown here are actually on the fingernails, on the fingertips. So you can imagine the control has to be very sophisticated. It is absolutely wireless operation, and it is a smart device. So we are making the devices, making the components smarter, more intelligent, more autonomous. Okay, then how it is done? It is being done by drastically increasing the sensory data, advanced sensors. In fact, the advanced sensors also are being manufactured by micro manufacturing techniques, and these miniaturized sensors can be accommodated in the small areas. So it ultimately, if you see, it boils down to the sensors, which are again very small size. Previously, the sensors were bulkier, larger size, but then nowadays, when you have the capability to manufacture those sensors at a very miniaturized scale, right? Downsizing significantly, you are able to introduce more number of different types of sensors in a particular component, making it more intelligent, making it smarter and autonomous. Okay. And then having said that, you have to keep it in mind that you are doing the downsizing, you are doing the miniaturization of the electronic components. At the same time, you should not forget about the one very important fact, that cost and energy consumption. If you are increasing the cost by doing all these things, you are miniaturizing, but at the same time you are escalating the cost. You are doing the miniaturizing, but you are escalating the energies, okay, energy consumption of the device. Then there is of no use. Your components are intelligent, your components are smarter, your components are the products are autonomous, more autonomous, but then it is hugely costly, okay, non-affordable, okay, then it is of no use. If the energy consumption is very high, then it is of no use, right? So it has to be energy efficient, it has to be cost efficient, and these two things are very, very important parameters in industry. For us, the academicians, the researchers, we often do not give much emphasis on these two aspects: cost, productivity, energy consumption, etc. We rather put our more emphasis on development of some technology, improving the quality of the product, and so on. But then productivity, cost, and energy consumptions are the major requirement from the industry that should not be sacrificed while we are doing the miniaturization. That is very important aspect. Okay, I have given many examples, but then again quickly I would like to tell you that it has now a lot of applications. These miniaturized components, which can be manufactured by micro manufacturing techniques, have a lot of applications in biomedical and bio-MEMS. These are very bio-MEMS is a very emerging areas where micro electromechanical systems, in fact, lot of micro electromechanical systems can be developed for biomedical applications. This is called bio-MEMS. Even not why micro, it has now gone to nano level as well. From MEMS, it has gone down to NEMS. That means nano electromechanical systems. I mean, let me tell you, this topic, that's why introduces us to a very fascinating world of manufacturing, where there will be a very paradigm shift. I mean, we are observing in the last 10 years how there is a revolution in the concept of manufacturing, in terms of downsizing of the components, in terms of making more smartness, more intelligence, and more autonomous features. Other examples, as I said, micro tools for surgery. There are a lot of micro surgical tools which are available nowadays. However, again, in India we are lacking. Let me tell you, I have been focusing, I have chosen this topic very specifically because this is one of my fascinating research areas where I have been doing a lot of work nowadays. Okay, because in India, there are hardly any manufacturers, indigenous manufacturers, who develop these micro tools for surgery. Many times we have to import these surgical tools from abroad, and they are hugely costly. But then if we actually can develop some micro manufacturing technology in a wide scale, in an industrial scale, right, then we will be able to develop, come up with a lot of startups, okay, and industries to indigenously develop so many miniaturized components for various applications, okay, molds and medical components, lab on chip. You see, some of you might have heard about the concept of lab on chip. I mean, basically you are developing the chips, and you are downsizing the chips, and you are creating a kind of lab, right, a laboratory setup. For example, a microfluidics. Okay, so when you are when you want to visualize the microfluidic phenomena occurring, right? So those this laboratory setup, the experimental setup, can be built, can be developed in a small circuit-like thing, where you have the as it is shown, right? As it is shown here, this thing, these micro channels, and all connected by these small devices, where actually you are building a lab, virtually building a lab on a small chip. That is concept of lab on chip, which is actually basically connected to the microfluidics applications. But then, having said that, in lab on chip, you will find out all these components in a miniaturized scale, whether it is a micro channel, whether some other micro valves, okay, micro actuators, okay. So all these things are the components which need to be manufactured by micro manufacturing techniques, right? Similarly, other dental brackets, then dental implants, or any other biomedical implants, we require extensive use of micro manufacturing, right? Not only in this in the domain of, for example, I mean, medical or biomedical applications, even the watchmakers, jewelry, okay, watch base plates, molds for rings and pendants, etc. I mean, you can see the figures. So basically, these are all the small features, complex 3D features, which I have already discussed in my previous slides, can be are actually need to be developed, which requires micro manufacturing technique. Okay, so this completes my application side, okay, which I felt is very important to highlight, so that we understand what is the requirement of micro manufacturing nowadays, particularly, and more particularly in India. Okay, so one particular application I would not like to skip, right? Having discussed all these applications in nowadays, etc. Nowadays, we are talking about this micro manufacturing or mechanical micro machining, talking about these trends of miniaturization, developing a lot of miniaturized components. Can anyone tell me, okay, in the audience, that which was the first country, okay, which started the concept of micro manufacturing at a very old age? Whatever I am talking about, this is the development in the last 10 years. But let me tell you, even 40 years down back, there was still the concept of micro machining, but not many people were aware of that. Very small, it was actually restricted to very small groups in industry or researchers, and they did not disclose their technology of micro machining or micro manufacturing to others, and therefore the world was not aware of this concept of micro manufacturing. Can anyone please tell me who was the country which actually gets the credit of developing this micro manufacturing technology, and what is their product? There is one particular product, okay, that was perhaps one of the first products. I cannot claim that this is the first product, okay, but because there is no documentation, written documentation on that. But in my opinion, this product is one of the primitive products, or the first products in the domain of micro manufacturing or micro machining. Can anyone please tell me who was the first country and who is the first product? Okay. Any answer? I cannot see the chat box. If someone would like to say something, they can just unmute and then tell me. I'll be happy to know the answer. It is very interesting. In fact, I mean, all of you, I think all of you know the product. Okay.
Sir, heart stent.
Sorry?
Stents, blood stents that you used for blood blockages in veins.
Stent, right?
Huh?
Stent. Okay.
Yes.
I mean, heart stent. Okay. Heart stent. Yes. Heart stent is one of the applications of micro manufacturing. I completely agree with that. But then stent manufacturing, I don't know exactly when the stent was first developed. I don't have much knowledge about it, but then I don't think it was developed 30-40 years back or 50 years back. Is it so, the stent? If yes, then it is also one of the first products of which required micro manufacturing. But stent, I think it was developed some 20-25 years back, not 30-40 years back. I'm talking about some product which was 30-40, even 50 years back. I don't know exactly. Some, of course, some 40-50 years back, those products, and very famous. Stent is a very limited application, but that product is a very, very famous product. Okay, so let me tell you, that is just the watch. Okay, either wristwatch. Okay, primarily the wristwatch, and that is the what I am talking about is the Swiss watch made by Switzerland. Okay, watch made by the Switzerland was developed. I do not know exactly. You can search in Google. You can immediately find it. It is definitely 40-50 years back, or even earlier than that. Okay, so Swiss watch, why it is actually very, very expensive. Swiss watch used to be expensive. Now nobody talks about this Swiss watch, right? Because there are so many other watch manufacturers, so it has actually reduced the glory. But now, I mean, when I was in my childhood, I mean, or my fathers or their generation, they are fascinated about this Swiss watch, and it was absolutely expensive. What is the reason? Reason is Switzerland was among the first country. I cannot claim it is the first country. Maybe some other country was also doing it confidentially that nobody knew. But what my understanding is, Switzerland was among the first countries who developed this concept of micro machining. Okay, they used to develop the components of the watch. For example, micro gears. Micro gears were developed by the watch manufacturers in Switzerland. This is absolutely in the micro scale and a very, very precision level. How it was made, these micro gears? By micro manufacturing. And they did it. They had that technology. They had that machines. But only thing is that nobody knew about it. They never disclosed this technology to outside world, and outside world was absolutely unaware of this fact. So this so truly speaking, micro machining or micro manufacturing is not a new concept. It is an absolutely age-old concept. But only thing is that why we are talking about micro machining sitting here in 2021, okay, is only because it has become popularized only in the last 10, 20, 15 years. And then in the last 10, 15 years, I mean, the scale, the rate of growth of the miniaturized components is massive. Why? Because nowadays, the world is now aware of the micro manufacturing technologies. There is no confidentiality. People can manufacture the micro gears very, very easily nowadays. If you have the technology, you can actually make the watch. I mean, a Swiss watch can also be built in India, and therefore it has lost its glory. I mean, there is, but then nowadays it is fine. But then you imagine, I am talking about 1960s, 1970s, 1980s. Micro machining was existing, and the technologies were known by the Swiss watch manufacturers. These are very, very fascinating information. Okay, coming to the topic again, this the classification of micro machining. So when we are talking about the micro machining, right? There are two types. One is the traditional micro machining. Traditional micro machining, and another is the advanced manufacturing, advanced micro machining. Okay, so what is the traditional micro machining? Traditional micro machining is the primarily the mechanical micro machining. It can be also called as the mechanical micro machining, like micro turning, micro milling, micro drilling, because these are the technologies which requires which are basically based on the conventional machining techniques, right? Because turning, milling, drilling, they are all conventional technique. But then by miniaturizing these processes, we are getting micro turning, micro milling, micro drilling, etc. There, called as the traditional micromachining. They are also called as mechanical micromachining, right? Similarly, if you are talking about this advanced micromachining, advanced micromachining, then it is primarily it is based on the non-conventional machining techniques. All of you know the non-conventional machining techniques like abrasive jet machining. Let me just focus. Abrasive jet machining, then abrasive water jet machining, then ultrasonic machining, right? So these are the non-conventional machining technique, and with the development of technology, all these three things like abrasive jet machining, abrasive water jet, or ultrasonic machining can be also downsized to call it as the micro machining. For example, ultrasonic micro machining, abrasive jet micro machining, abrasive water jet micro machining. So they are actually come under the subtopic of mechanical micromachining, but then under the advanced micromachining domain. See, this mechanical micromachining is also there, okay, when you are talking about this traditional micromachining, right? Like microturning is also a mechanical micromachining. Micromilling, microdrilling are also mechanical micromachining. But then there are certain micromachining techniques which come under the advanced micromachining technique. So I hope you understand that these two differences. Similarly, the other micromachining techniques can also be classified in terms of the energies which are used. So in the first topic, we are using the mechanical energy. Similarly, we can use the thermal energy to develop thermal micromachining techniques. Electron beam micromachining, laser beam micromachining, electro discharge micromachining. Okay, all are micromachining domain, right? Similarly, chemical, if you are using the chemical energy some way or the other, then it is called chemical micromachining. Then photochemical micromachining, electrochemical micromachining, where we require directly or indirectly the chemical form of energy to do the micromachining, right? So okay, basically when I would like to discuss a little bit about the processes, okay, very introductory, and then I will finally go to this traditional micromachining, because this is the the work that I have been currently doing, traditional micromachining, particularly in the domain of micro milling and micro drilling. Okay, so what are they basically? So micro turning, if you see, so there are dedicated machines. This is called diamond cutting machine, right? Single point diamond tool. Single point diamond tool is used for micro turning. Okay, why diamond tool is used? Because diamond is a very hardest material, and it can actually maintain its sharpness at the very low level, micro nano level. Okay, atomic level sharpness is possible to be maintained by the diamond tool, and therefore this as far as the micro turning is concerned, it is typically done by single point diamond tool. Okay, and there are a lot of research work which is going on in the domain of this micro turning. Now, what is how micro turning and how it is different from macro turning, right? As I said, primarily you are downsizing the features, right? For example, you need to create a cylindrical surface of 5 millimeter. Okay, so then conventional cutting tool cannot be used to create a cylinder of 5 millimeter because it is that small. So you have to take the help of micro turning operation, where you can actually bring down the depth of cut. Typically we are using 0.5 millimeter, 1 millimeter, 2 millimeter, 3 millimeter. You can actually bring down the depth of cut from those millimeter to microns. You can set 10 microns, 20 microns depth of cut in micro turning operation. Similarly, feed. Okay, feed in turning operations typically varies from say 0.05 to 0.3 millimeter per revolution. Okay, 0.05 to 0.3 millimeter per revolution. This is that standard range of feed what is done in macro turning operation. But here we are talking about micron per revolution. 1 micron per revolution, 2 micron per revolution, 3 micron per revolution. I am talking about the feed. So you see how the depth of cut and feed are being downsized in the micro turning operation. And that is the one of the major difference between the macro and micro machining. And when you are talking about the turning, it is the difference between micro and macro turning. Now the thing is, micro milling, same thing. Micro milling and micro drilling, you can actually reduce the size of the cutter. We are talking in macro milling, we are talking about say 10 millimeter cutter, 50 millimeter cutter, 100 millimeter cutter, 200 millimeter cutter. In micro milling, we are talking about 0.5 millimeter cutter, 1 millimeter cutter, 0.4 millimeter cutter, 0.3 millimeter milling cutter. And similarly also, the same thing goes for drilling operation as well. But at the same time, I must highlight, it is just not downsizing the the dimension of the cutting tool, but at the same time, the feed and depth of cut. Feed and depth of cut also need to be considered in a micro level. Then only it will be qualified under the domain of micro machining. I hope you are getting the point. Similarly, if we are talking about the advanced micro machining technique, then again, many people know about this electro discharge machining and electrochemical machining. So I can take the help of this electro discharge machining and electrochemical machining to discuss about this micro machining concept. See, it is the same concept, right? Let us take the example of electro discharge machining. Okay, but when you are actually downsizing to make it electro discharge micro machining, what is the requirement? Requirement is to drill a hole. For example, if you are creating a hole using electro discharge machining, then a micro size hole. For example, you want to develop, you want to drill a hole of 100 micron diameter, 200 micron diameter, 300 micron diameter, or even less than that. That is called micro electro discharge machining or electro discharge micro machining. I hope this point is clear. Now, it similarly for electrochemical micro machining also, it is just comes down to downsizing the dimension of the tool that you are using, right? So apart from downsizing the tool that are used for EDM and ECM, there is another aspect which needs to be taken into consideration, the parameter. Parameter is also very important, which distinguishes from macro machining to micro machining. Okay, in micro turning, micro milling, micro drilling, I have talked about feed and depth of cut, how they are actually, reduced from macro level to micro level, their values, and that actually makes it micro cutting, micro machining, which is distinct from macro machining. Similarly, in EDM and ECM also, you have to be a little bit careful about the parameters. For example, in EDM, okay, we are using high voltage, low current, right? In EDM, right? What is the voltage? Voltage is 50, 60, 70, 80, 100 volt, something like that, right? So, but here, when you are actually going for the micro electro discharge machining or micro EDM, then you have to be careful that the energy that you are supplying. When you are talking about that voltage and current, I am actually talking about the energy, electrical energy, energy input that is responsible for material removal, that is responsible for spark generation, right? Now our intention is to have the micro machining, so we have to reduce the input energy in such a level that we get the micro machining realized. I hope this point is clear to you. If you have any doubt, please don't hesitate to interrupt and then ask me questions, your queries. So that means your voltage needs to be reduced, okay? And then some other voltage in micro EDM also we use resistance capacitance circuits, RC circuits in modified form, of course. Resistance capacitors also can be controlled. Voltage that can be also controlled, so that I mean you can limit your input energy to a minimum level. If you are actually try to go for high energy that you typically use for macro EDM, then what will happen? Your tool will be melted, right? The tool has, for example, the dimension of 100 micron, because you want to drill a hole of 100 micron size. So you need to take a tool of 100 micron diameter in EDM, micro EDM. So the 100 micron tool will may become melt because of this energy which is being passed through the tool. So you have to reduce the energy. Similar technique goes to the electrochemical machining as well. As you know that ECM is a high current process. In macro ECM, what is the typical range of the current we use? 500 ampere to 1500 ampere. Can you imagine the such a high level of amperage is required to realize electrochemical machining process? Material removal rate, as you know, that is directly proportional to the current. And if you want to increase the material removal rate, you need to increase the current. And this is the typical range, 500 ampere to 1500 ampere, which is very, very huge. But when it comes to the electrochemical micro machining, you have to reduce the current requirement. You have to have the pulsed supply, so that the energy which is being provided is in a pulsed form, not in a continuous form. So there are modifications. What I want to emphasize through the slides, that there are various types of micro machining processes, and then ultimately it goes down to the downsizing the tool. It goes down to downsizing the features that you are creating through the processes, and last but not the least, it is downsizing the parameters which are responsible for this machining action. Whether it is a non-conventional machining, micro machining based on non-conventional concept, whether it is a micro machining based on the traditional machining concept. So, I mean, the concept remains same. Okay. So okay. So so from now, in the last, for example, half an hour, I would like to devote myself in the basic concepts of mechanical micro machining. Mechanical micro machining under the traditional micro machining domain, not in the advanced micro machining domain, right? Because that is the research work I currently am working. Okay. So again, as I am saying that I do not have the opportunity to show you the research work, but rather I thought it is very important to first of all discuss about the fundamental aspects and the requirement of the micro machining. So I will devote myself in the next half an hour in the mechanical, I mean the fundamental aspects of traditional micro machining, that is the mechanical micro machining. Okay. So here, I mean, the most important aspect which distinguishes it from the macro machining is the size effect. And the concept of size effect, I would like to discuss it in little bit detail. But before that, let us talk about, just as a recapitulation, all of you know, that is the Merchant theory for macro machining. In our undergraduate metal cutting course, we have learned about the Merchant's theory, okay, but that was actually, applicable for macro domain. What are those assumptions? If you recall, cutting edge was perfectly sharp. Cutting edge was perfectly sharp. There was no contact between the tool and the workpiece material along the clearance surface. Okay. Right? Because of the flank wear, there is a contact which gets developed between the flank surface and the workpiece surface. Okay, that we also neglect in the Merchant's theory. Cutting edge is absolutely sharp. If we, I'm sorry, this. So this is the tool. Okay. So this is the section of the tool. I think all of you are aware of this section of the view of the tool and the work. This is the workpiece. This is the workpiece. I mean this part. This part basically. This part is the workpiece, and this is the chip. This is the chip, and this is the shear plane or shear zone, right? Where the chip formation is taking place. Okay. So our assumption is it is perfectly sharp. So that means there is no edge radius present here. Let us focus your attention here. There is no edge radius present here. Okay. We are not considering. Material is very rigid and perfectly plastic. Okay, there is no elastic deformation involved, and there is no side spread of the chip. There is of the material. That means it's a plane strain condition. Okay, so material is predominantly removed by mechanical shear force due to the interaction between the sharp tool and the workpiece, and therefore forming a chip. Okay, so this is the fundamental aspects of merchant theory, which was responsible for all the analysis of the cutting operation, metal cutting operation, orthogonal cutting primarily, and then the deviation of the orthogonal in the form of oblique cutting that you all know of. I am not going to discuss all those things. Now the question is, when you are going to the micro domain, this merchant theory is not valid anymore. Merchant theory is not valid anymore. Why? Because the radius of the cutting edge suddenly becomes very significant. Suddenly becomes very significant. So this is the conventional machining. I'm sorry. This is the conventional machining. Okay, conventional machining. You see, the cutting tool is very sharp, and then it generates the chip. Exactly the figure that I have drawn in the previous slide. But then this is the micro cutting. This is the micro cutting. The next figure. Okay. Here you see suddenly the radius of the cutting edge becomes very significant. Okay. Now why it becomes significant? It is simply because of this uncut chip thickness. Uncut chip. What is uncut chip thickness? Uncut chip thickness is this one. This is the uncut chip thickness, right? And here, this is the uncut chip thickness. This is the uncut chip thickness. Okay, it's very, 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 very small. In macro machining, that means I am talking about in this figure, the uncut chip thickness is in the order of millimeter. It can be half a millimeter. It can be 1 millimeter. It can be something like that, right? In terms of few hundreds of microns, you can say few hundreds of microns, either 300 micron, 500 micron, 1000 micron, so on and so forth. Macro machining, conventional machining. But in micro machining, this uncut chip thickness becomes very, very small. Now, if you ask me how much small, it is in the range of few microns. 1 to 2 micron, 3 micron, 4 micron. Try to understand the difference. In macro machining, the uncut chip thickness we are talking about in the range of few hundreds of microns. In micro machining, the uncut chip thickness we are talking about few microns. What is the reason? What is the reason? Reason is as follows. In macro machining, we are talking about the feed which is very high. As I just now talked about, what was the range of feed? It is, for example, 0.05 millimeter per revolution to say 0.3 millimeter per revolution. That means 50 micron per revolution to 300 micron per revolution. Here we are talking about 0.5 micron per revolution to 10 micron per revolution, or 12 micron per revolution. That is the range. 0.5 micron to 10 micron per revolution. So you can understand there is an order difference. Okay, and this uncut chip thickness is directly correlated with the feed. I repeat, uncut chip thickness is directly correlated with the feed. From the concept of metal cutting, you know it very well, right? F of sine F into uncut chip thickness equal to F. I do not have the pen to write here on the screen, but just that's why I am trying to say it verbally. So please bear with me. Okay, so uncut chip thickness is equal to F into sine phi, and where phi is the principal cutting edge angle. Okay, F into sine phi, phi is the principal cutting edge angle, right? So this is the uncut chip thickness. So you understand, uncut chip, higher the feed, higher is the uncut chip thickness. Lower the feed, lower is the uncut chip thickness. In micro machining, we are actually using very low feed, so very low uncut chip thickness. Why we are talking about putting a lot of emphasis on uncut chip thickness suddenly? I mean, the answer is very simple, but then very important to understand as well. The value of the edge radius, I repeat, the value of the edge radius and uncut chip thickness are of the same order of magnitude in micro cutting. In micro cutting, the edge radius of the tool is of the order of 2 to 3 micron. Even the uncut chip thickness is also around 1 to 5 micron. Around 1 to 5 micron uncut chip thickness. Okay, so that means you see the edge radius and the uncut chip thickness, they are of the similar order of magnitude, and therefore the radius of the tool gets amplified. The effect of the radius of the tool gets amplified in the micro cutting domain. Okay, in the micro cutting domain, right? But then what happens in the macro machining? In the macro machining, it has the edge radius. It has the edge radius, and edge radius is typically ranges from 10 to 50 micron. 10 micron to 50 micron radius of the cutting edge. But then why it is considered as sharp by merchant? Because the uncut chip thickness is hundreds of microns. If the edge radius of the macro cutting tool is 10 micron, then the uncut chip thickness is 300 micron, 400 micron, 500 micron. You see that there is an order difference between the edge radius and the uncut chip thickness. But in micro cutting, they are of the same order of magnitude. Now, what is the implication in terms of mechanics when the cutting edge radius and the uncut chip thickness become of the same order of magnitude? There will be the rubbing action. There will be the plowing action, right? I mean, it acts like a blunted knife. For example, if you want to chop a vegetable with a blunt edged knife, then you will require a lot of forces, higher forces. You require a lot of energy to chop the vegetable compared to when it is very sharp, right? So exactly the same thing happens here in the micro cutting. Although the edge radius is very small, but at the same time, the uncut chip thickness is also very small, and therefore it acts like a blunted cutting. And when it acts like a blunted cutting, the rubbing and plowing becomes very, very significant, and then shearing becomes insignificant. Shear deformation. And until and unless shear deformation takes place, you will not have the chip formation, even in the micro cutting regime. And that makes it very, very complex affair. And that is what is called as the size effect. Okay. this is about this cutting edge and the uncut chip thickness. But there is another point. What is the the grain? That is the grain size. We have talked about the radius of the cutting edge. We have talked about the uncut chip thickness, their values. And now I am talking about the grain size. Three things. Even grain size is also comparable to the uncut chip thickness or undeformed chip thickness. So in summary, you find out what is the, so before that, what is the grain size of the tool material? When I am saying the grain size, it is not the grain size of the, workpiece material, right? The workpiece material or the tool material, whatever. The grain size is in the range of 1 micron, 2 micron, 5 micron, 10 micron, like that. Grain size. What is the undeformed chip thickness? Again, 1 micron, 2 micron, 3 micron, etc. What is the cutting edge radius? In the same order of magnitude. So three things are of the same order of magnitude: grain size, edge radius, uncut chip thickness. And that makes the things complex, because this rounded cutting edge actually attempts to fracture a single grain. And that's why when you are actually trying to attack a particular single grain, it will encounter or it will experience more resistance. The grain will offer more resistance compared to the grain boundaries. Okay, grain boundaries, as you know, is weaker, and the deformation takes place through the grain boundaries, and it is easier because that is the weakest path. But then when you are encountering a single grain, then it becomes difficult to cause fracture or deformation. Since the cutting edge radius is of the similar order of magnitude of the grain size of the workpiece material or the tool material, right? Then it becomes very, very difficult to cut. And as a result, specific cutting force and specific cutting energy becomes very high in micromachining. Again, my last statement is very important. Specific cutting force, specific cutting energy is quite high in micromachining. In macromachining, it is not the case. Why it is not the case? Because the undeformed chip thickness is very high compared to the grain size, compared to the edge radius. Therefore, they are not considered in the chip formation mechanics. But in micromachining, you have to take care of the grain size and the edge radius in the analysis or in the mechanics of chip formation. Number one. Number two is negative effective rake angle prevails, right? When you are talking about this rounded cutting edge, see in the second figure, rounded cutting edge. So the effective rake angle, let me just rub it again. So just focus your attention on the second figure. The effective rake angle. Ultimately, what is the rake angle? Ultimately, what is the rake angle? Alpha. Alpha is the rake angle, right? You know that. Alpha is the rake angle here. Alpha is the rake angle in the micro cutting, macro cutting, whatever. But when you are considering this, high edge radius, it is actually the, see, this is the effective rake angle. And this effective rake angle becomes highly negative. And what is the repercussion? What is the implication of the high effective rake angle? High cutting force. You know it very well. When the rake angle becomes more positive, cutting force is less. When the rake angle becomes higher and higher on the negative side, cutting force becomes more. But then it strengthens the tool, but that is a different issue. But then cutting force is high. Energy will be high. Specific cutting energy will be high. What do you mean by the specific cutting force? It has two definitions. One is the force to remove unit volume of material can be considered as the specific cutting force. Similarly, specific cutting force can also be defined by the force per undeformed chip area. I repeat, specific cutting force in micromachining can also be defined as the force divided by undeformed chip area. And why the specific cutting force is very high in micromachining? Simply because the undeformed chip area is very, very small. Why undeformed chip area is very, very small? Because the undeformed chip thickness is very small, and therefore, since the undeformed chip thickness is small, so the cross section of the undeformed chip area, that is also very small, and therefore the net effect is specific cutting force is very high, right? And then multiple material phases exist because workpiece actually consists of different phases. It is ultimately an alloy, and therefore there are different phases present, right? Pearlitic, if you are considering steel, martensitic phase, pearlite phase, ferritic phase, etc. Exist at different locations. If you are considering the inconel, then gamma prime phases exist. So different phases exist even in a single material at a very micro scale. But when you are actually doing the macro machining, inhomogeneity, microscopic inhomogeneity present in the workpiece gets nullified. But in micro machining, this microscopic inhomogeneity present becomes highly amplified, making it a challenge. And then force increases, not force increases. The specific cutting force increases, the specific cutting energy increases. Okay, so if I want to distinguish between micro machining, macro machining, although I have told a lot of things already, but this is perhaps the summary, and one or two things are new in this slide. That microstructural level I have talked about. Just now I have talked about what is the difference between micro machining and macro machining. In micro machining, we are attacking a single grain, and therefore the resistance is high. The resistance to deformation when you are attacking a particular grain will be higher. Rather, the grain boundaries are weaker. In macro machining, the deformation takes place through grain boundaries, right? Why grain boundaries? Because the undeformed chip thickness is very high, and the area of contact is on a very larger area, and therefore grain boundaries are being encountered, not a single individual grain, and therefore deformation is easier. Tool dimension I have already talked about. I am not repeating. The feed I have already talked about. I am not repeating. Exactly the same thing this has been done. Minimum chip thickness is something I need to talk about. But then first of all, let us talk about the speed. When I am talking about speed, I am talking about actually N, that is the RPM, spindle RPM, not the cutting speed. Let me tell you, when I am talking about the speed, differentiating between micro machining and macro machining, I am primarily focusing on the spindle RPM. In micro machining, the spindle RPM in most of the cases very high, 20,000, 30,000, 40,000, even 1 lakh, 1.5 lakh. It is that high. And when you are talking about this macro machining, okay, it is, although it is written 10,000 RPM, let me tell you, this is actually 10,000 RPM are mostly not used in macro machining domain. What is the typical RPM in when you are doing the turning operation? 200 RPM, 300 RPM, 500, 600 RPM. When you are doing the drilling milling operation, what is the RPM? Same thing, maximum 1000 RPM. Maximum 1000 RPM or 1500 RPM. So that is the working range of RPM what we are dealing with in the macro machining domain, right? What is the reason? The reason is its tool diameter is very high. If it is a turning operation, the workpiece diameter is very high, and therefore to have a particular cutting velocity, for example, you need to have the cutting velocity of 50 per minute, 50 meter per minute. Okay, to achieve the cutting velocity of 50 meter per minute, you need much lower RPM in macro machining, since the workpiece diameter is very high. If it is a drilling milling, since because the tool diameter is very high. But to achieve cutting velocity equal to 50 meter per minute using a drill diameter of 200 micron, some of you can actually calculate, okay, using the formula VC equal to pi dn by 1000, okay, you will find out the requirement of RPM is many fold higher. And that is the reason why spindle RPM is very high in micro machining. I hope this is clear. If you still have any doubt, please feel free to ask me. Okay, there is another concept for what is the minimum chip thickness. Minimum chip thickness or minimum undeformed chip thickness rather. Okay, so it is written that depth of cut should be greater than critical chip thickness, and chip thickness before cut should be greater than the chip thickness before cut. Chip thickness before cut should be greater than chip thickness after cut. Okay, so this statement might be a little bit confusing. So to discuss it further, I will go to this size effect diagram. Okay, and I think this will be my last slide in my presentation today. So if you see, so this is the amplified view of the diagram that I have shown in my previous slides, right? So okay, so you see there is a, because of this edge radius effect, there is a plowing. Okay, so just a minute, I'll just take a break of a few seconds. Yeah, I am back again. I hope my screen is again visible. So I was talking about this plowing dominant thing. Now, when let me tell you, please try to understand that when this undeformed chip thickness is very low, very low, then what happens is there is actually the material strengthening or stagnation which takes place in front of the tool. Okay, just like in agriculture, plowing, what we have seen, that it is no material removal, rather it is getting side flow on both the surface, on both sides material flows out, right? But no material separation takes place. When the undeformed chip thickness is very small, then actually the radius of the curvature of the cutting edge becomes predominant, and then it tries to push the material ahead, and then there is no shear deformation. And then when there is no shear deformation, there is no chip formation. So what is our objective? Objective is to have the chip formation, even in the micro cutting. So to have the chip formation, what is the requirement? Requirement is we should have the shear deformation, predominant shear deformation, and minimal amount of plowing and rubbing. Okay, rubbing and plowing is something which will be very difficult to eliminate altogether in micro cutting regime, but you can always minimize it so as to have the chip formation by shear deformation, right? To have that, you have to achieve a minimum undeformed chip thickness. If your undeformed chip thickness is higher than this threshold value, you will have shear dominant deformation or chip formation. If your undeformed chip thickness is lower than the threshold value, okay, that is the critical value, then you will have predominant plowing and rubbing action and very less shear deformation, okay, and then you will have elastic deformation predominantly, less plastic deformation. Under what condition? When the undeformed chip thickness is lower than the critical value of the undeformed chip thickness, that is the minimum threshold value. So as an engineer, as a scientist in the domain of micromachining, we have to always ensure the fact that we are always ahead of the minimum uncut chip thickness. And the determination of minimum uncut chip thickness requires the knowledge of the mechanics at the micro scale. It requires the concept of modeling of forces in the micro scale, so that we understand what is the minimum uncut chip thickness at a particular condition, and accordingly we can adjust the feed. Ultimately it boils down to feed. You change the feed, you will change the uncut chip thickness. Ultimately your objective is to have plastic deformation in the form of dominant shear mode, not the elastic deformation dominated by plowing and rubbing. This is the most fundamental aspect in micromachining, which is governed, which is characterized by size effect. In macromachining, there is no size effect because the undeformed chip thickness is high, because the feed is high. But in micro cutting regime, the size effect dominates, and therefore it makes it challenging, and it actually leads to the high specific cutting energy. Okay, so this is the this is another figure for your information. So this is the conventional machining. Okay, I am just repeating the same thing again and again because this is the most fundamental aspects concerning the micro machining. This is the conventional macro machining. Chip thickness is 0.1 millimeter, or uncut chip thickness is 0.1 millimeter. But it is the precision machining or the micro machining where you see the edge radius, undeformed chip thickness, grain size, all single grain, and then there is a chance of elastic spring back because of this, because of these things. Only chip thickness is several microns, 2 micron, 3 micron, 4 micron, 7 micron, etc. And this is the undeformed chip thickness H. This is the three condition. That's what exactly I have talked about, right? That is the threshold value, critical value of undeformed chip thickness, below which you will have predominant, elastic recovery. Okay, so this is the condition where elastic recovery takes place. That is the elastic deformation takes place. Under what condition? When H is very, very small, undeformed chip thickness is very small compared to the edge radius, right? Then you see chip formation does not take place. But when we are increasing the undeformed chip thickness close to the value of the edge radius, then some material gets removed. Okay, and then when you are increasing this undeformed chip thickness still further, then you have significant material removal, because you see the chip formation is facilitated. Why? It is because this shear deformation becomes more predominant than the rubbing and plowing action. In other words, plastic deformation is more predominant than the elastic deformation. Elastic recovery is minimal. I hope these schematic diagrams are extremely helpful in understanding the fundamentals of size effect phenomena occurring in micromachining. Okay, so what is the effect of size effect? The size effect, cutting, it has the influence of the cutting force, it has the influence of the chip thickness, it is the influence of the chip formation, it has influence of the quality of the machine surface, small uncut chip thickness, cutting temperature, and okay, and high yield strength of the workpiece, right? High yield strength of the workpiece, because you are actually concentrating on the single grain. So these are the things I have already talked about, right? So the stresses applied to the tool are dependent on the individual grain orientation, because you are actually attacking a single particular grain. So I mean, grain orientation has major role to play. High frequency of fluctuation of the cutting force because of the inherent microscopic inhomogeneity, and last but not the least, it is a unstable and there is a chance of tool breakage. Why instability and tool breakage? As I said, there is a fluctuation because of the inherent microscopic fluctuation. There is a force fluctuation, and because and then tool size is very small. It is a slender. Its rigidity is very less. Okay, and therefore it cannot withstand the high specific cutting force, high specific cutting energy, high frequency fluctuation of the cutting forces, and there it is prone to breakage prematurely. These are the challenging aspects, and it requires a lot of research work to encounter, counter these problems, right? So these are some of the things. Since I do not have time, otherwise I could have, extended little bit. But most of the things I think I have covered as far as the fundamental aspects of, micro machining, particularly the mechanical micro machining. This slide shows the fluctuation of the cutting force that takes place in the microscopic level. Okay, so this is the diamond turning that I was talking about at the very beginning. Turning operation using the single point diamond tool at the micro to achieve the micro turning operation. So this is the specific cutting energy, and this is the graph. What is the effect of size effect, and why more energy and more cutting forces are needed to remove unit volume of cutting material in the uncut chip thickness. Okay, so this is all about today's lecture, and just in summary, I would like to tell you, I have talked about the necessity of the micro machining, its major applications of micro machining, historical perspective, why it is important, and its major classification of micro machining, and then I have focused only on a very small topic, that is the fundamental aspects concerning the mechanics of mechanical micro machining at a micro scale. So thank you for your kind attention, and if you have any query, please feel free to ask me.
Any question, please ask. You may put in chat box or directly unmute, directly ask to sir. Any questions?
So just for your information, the audience and also Dr. Santosh and Dr. Chittaranjan, that at IIT Bhilai, I have developed I have procured a high-speed micro machining center, okay, where students are doing a lot of research work in the domain of mechanical micro machining, high-speed micro machining. Okay, micro drilling, micro milling, even micro grinding can also be done. So if some of the students, some of the research scholars are fascinated or interested to work in that domain, they can feel free to talk to me, interact with me, and then if required, they can come here, see the facilities, and if some collaborative work can be done, it can be thought of.
Okay, thank you, sir. And thank you for sharing your expertise in micro machining. So especially we have learned from today class about the introduction of machining and application life on the use, watchmaker, jewelry, and then watch base plate, then mold of rings, pendant, anything. And also you have learned the micro machining classification. Then also you have learned about the merchant theory of micro machining, because already you have to know the motor circle in the normal manual science too in the BTech. And already you have know what is the difference between your micro machining and macro machining. And finally you have to learn about the size effect, like strain rate, temperature, then strain gradient. Then thank you, sir, which are very interesting. And I hope all the participants acquire the knowledge about the different techniques and new innovation in the area of micro machining. If still you have any doubt, you may contact to sir. Already sir announced them, and already sir has put his mail ID in chat box. Okay, thank you, sir. Sir, namaskar.
Yeah, thank you,
Thank you, sir.
Dr. Santosh, and thank you, Dr. Chittaranjan, for inviting me to deliver this. It was my pleasure to deliver a talk on this micro machining. I thought that it's very fascinating thing, and then this is the first time I'm delivering a talk at VSCCT Burla on this topic. I think many more students will take a lot of interest to enter into this fascinating area and then do some research work, which is a very, very emerging field worldwide. Thank you.
Thank you, sir.
Thank you, sir.